Okay. It's 2:02. I think we can start. So welcome everyone to the last webinar of 2020, to the last NITheP webinar. And our speaker today is Alexander Teretenkov. Alexander got his PhD from Moscow State University in 2017 under the supervision of Professor Chebotarev. And since then, he is working at Steklov Mathematical Institute, which is one of the leading, or probably the leading mathematical institute in Russia, and probably one of the leading mathematical institutions internationally. And we're very happy that Alexander will tell us about Markovian approximation of non-Markovian dynamics in all orders of perturbation theory, which is one of the, as probably you know, is one of the subjects which of interest to our group, and probably that will allow us to establish some collaboration. Okay, Alexander, it's your show.
Well, thank you very much. Thank you very much for the opportunity to give a talk at this webinar. Well, I will start with the outline of my talk. Actually, the main idea is the following. I will consider very simple, very well-known model, but I will do a different asymptotic analysis of it. Namely, the model which I consider is the spin-boson model in the rotating wave approximation at zero temperature. This model is in certain sense exactly solvable. It's used as a basic example for in the discussion of time-convolutionless master equations in Breuer and Petruccione book. And this is why I have analyzed exactly this model. And I will use the asymptotic analysis based on the so-called Bogolubov-van Hove scaling. So first of all, I will state the problem. I will tell you what all these terms means, like Bogolubov-van Hove scaling and so on. And then I formulate my main results. After that, I will go into details and discuss the initial conditions, the correlation function, and I will show some images about the results, and then I go to the conclusions. So first of all, I consider the Hilbert space of the two-level system and usual bosonic Fock reservoir. So I define sigma plus. I have usual definitions of sigma plus and sigma minus operators in C2, and I have usual definition of creation and annihilation operators dependent on the momentum with vacuum state, which I will denote by VAC ket vector. So I consider the Hamiltonian of the two-level system interact with the reservoir in the rotating wave approximation. Namely, I have only terms sigma minus B dagger here, but no terms of the form sigma plus B dagger and their conjugate. And I consider the Liouville-von Neumann equation with initial state, with zero temperature initial state, that is, the reservoir is in the vacuum state and the system in the arbitrary state initially, and they are not correlated. It's just a tensor product. So for sure, I have a coupling constant here, and of course it could be taken into this g of k, but I will separate it from g of k. Moreover, which is most important for my talk, I will use this small parameter not only in the coupling constant, but in the time rescaling. Namely, I go to the interaction picture. Here, the reservoir is invariant under the free dynamics of the reservoir. I mean, reservoir state, the vacuum state is invariant under the free dynamics of reservoir. So it is possible to go to the interaction picture after the tracing out, the reservoir degrees of freedom. Then I introduce so this is just the reduced density matrix in the interaction picture. And then I introduce the rescaled reduced density matrix in the interaction picture, which is defined as the follows. So I have not only this dependence of lambda defined by the small coupling in the Hamiltonian, but also I have this small parameter in the time, and I work with this rescaled matrix. The dynamics of the reduced density matrix with such a rescaling usually called Bogolubov-van Hove limit. And from physical point of view, this scaling allows one to separate the time scale on which the Markovian dynamics occurs from the time scale of order of the reservoir correlation time. From the mathematical point of view, I think it's most rigorous approach. Most rigorous approach to the mathematical justification of the equations in the weak coupling limit, and for the reduced dynamics, it was firstly, of course, already Bogolubov and Van Hove have derived the equations in Bogolubov-van Hove limit, but in more modern and more strict mathematical style, it was done by Davis here for reduced dynamics. And moreover, in this, for example, in this Accardi, Lou, and Balovich book, it is discussed how one could derive the stochastic but unitary dynamics of the whole system and reservoir in this limit. So, and also you could obtain the equation for the reduced density matrix by tracing out the stochastic operators. But what this is actually why I use this rescaling, because it was shown from this mathematical part of the story. It was shown that it's most rigorous and most direct way to derive the equations of both reduced density matrices and of stochastic evolution of both system and reservoir. They lead to usually to Gorini, Kossakowski, Sudarshan, Lindblad form equations, which occurs in weak coupling limits. Not many things done about corrections, asymptotic corrections to this limit, because here only in both in papers by Davis and by Accardi, Liouville-von and many others on quantum stochastic limit, they consider only the case when you goes exactly into these limits lambda to the turns to the +0. But what I'm interested in to derive the full perturbation theory in this with this Bogolubov-van Hove scaling. Some results actually are done in these articles by Pechin and Balovich, but the problem that we have obtained also the stochastic dynamics of both system and reservoir, but it was based on the called multiple noises, the noises which are correlated not only delta function but on the derivative or any derivatives of delta functions. And it is usually it is not very easy to obtain the equations based on this stochastic equation with this not delta correlation noises, but not delta correlated noises, but the noises correlated to the derivative to the derivatives of the delta functions. So I consider only the reduced dynamics without the stochastic dynamics of both system and reservoir. And what is possible to show here, that in the case, if you have n+1 finite moments of the reservoir correlation function, then they exist the Gorini, Kossakowski, Sudarshan, Lindblad type equation with what is most important here, with time-independent coefficients. So we have here the following equation with if we allow the time dependence of the coefficients, it would be something of generic case for this model. And when you have if you don't put here this condition, then it's maybe more generic case. But what is important, what I'm saying here, that you could use only time independent coefficients. So exactly as in the limit, lambda turns to 0, but slightly normalized. So we have not exactly the same, of course, the same coefficients like in the limit, but we have the equation of the similar form, but with certain renormalized coefficients, and these coefficients are time independent. So then, if we have enough moments of the reservoir correlation function, then you could approximate with this precision the exact solution of this model for the reduced density matrix. So the evolution of the reduced density matrices could be approximated by evolution with evolution defined by the JKSL type equation with constant coefficients. If arbitrary moments exist for the correlation function, then you could derive these equations with arbitrary asymptotic precision. But what is important, I work exactly with this rescaled in time density matrix. I remind you that this row of T and lambda is actually have this time rescaling. So it is very important for these equations to use Bogolubov-van Hove rescaling in the perturbation theory. And it is actually, I think, very natural if you think about these dynamics described by GKSL form equation with constant coefficients as of Markovian dynamics, then it is really natural, I think, that if you have enough amount of moments of correlation functions, what mean physically that you have enough moments of the correlation functions? It means just that the correlation function is well localized in time. So, for example, if we have only zeros moment, but not have no higher moments, then it is this reservoir correlation function is usually has long tails, and if it is exponentially decays exponentially, it for sure has all the moments. So it is, I think, very natural that if you your correlation function is well localized in time, then you could describe it by Markovian equations. And the better you could localize it in time, the better, with the better asymptotic precision, you could describe it by Markovian equation. But it is, I think, this is the main result, and I think it is I think good part of story. But there are some payments for this very simple equation. This payment is in the initial conditions. Actually, this is important that this result is for fixed t larger than 0. So this approximate solution is not good if we consider the time scale near 0 time. For example, if you consider t of order of lambda squared by themselves, and this is usual situation in the singular perturbation theory called initial layer or boundary layer, depends on the problem you solve. Here, I think it's better to call it initial layer. That is the initial condition for this for exact density matrix actually do not coincide with the initial condition of the perturbative solution. Of course, it is possible to ask, maybe it is because we have only asymptotical formula, it is natural to ask, maybe I have chosen bad approximate solution, but it is possible to redefine it of order of lambda to the power of 2m plus 2. So it is possible asymptotically change it. So in such a way that this initial condition would be the same. But it is possible to prove that if the first moment of the correlation function is not 0, then they will differ of order of lambda squared. So for all the approximate solutions in all orders larger than 1, we have sufficient divergence between the exact initial condition and the approximate initial condition. So it is really important to redefine this initial condition. Moreover, if this real part of this first moment of the correlation function is larger than 0, then these approximate initial conditions for the initial conditions for the approximate solution, even not a density matrix. So we have it is not it's from physical point of view, it is seems slightly nonsense that you have to use the initial condition, which is not physical, which is not even in density matrix here, to obtain better precision for this perturbation theory. And of course, it is also possible to discuss. Maybe it is possible to ask if it is if one could just redefine it of the order of lambda to the power 2m plus 2 to obtain a density matrix. The answer is no. So it sufficiently differs from any density matrix. So it is sufficiently unphysical initial condition. But of course, as I said, this approximation do not work on the time scale of order of lambda squared. So it's from physical point of view, this approximation does not work on in the initial region of order of correlation of reservoir correlation time. So one cannot apply this approximate solution in this small initial region. And so, but after this small initial region of order of lambda squared in this asymptotic theory, the approximate solution becomes well-defined density matrix, and it becomes physical for arbitrary initial condition. I mean, for arbitrary exact initial condition at time 0. Well, to understand maybe better this situation, first of all, let us here's a general formula for this time after which our matrix become a real, actually a density matrix, and let us understand what's going on in this for very specific spectral densities, namely the combinations of Lorentz peaks. In this situation, this T star could have the following form. So we have a weighted combination. Moreover, it's weighted with by relative intensities of the Lorentz peaks. Weighted combinations of these terms. Namely, we have 1 over gamma L, which is the reservoir correlation time for if we have only one Lorentz peak, so it is possible to interpret this combination without the last term as just as the reservoir correlation time here, because we have just weighted combinations of the correlation times for the separate peaks. And this term, which defines certain resonance condition of the existence of this time. Namely, if we have exact resonance, then this time is positive, and moreover, it's just the correlation time. But if we have we go far from resonance, then this time become negative. So we actually have no such unphysical region. So this unphysical region occurs exactly in the situation of the resonance condition. So, and from this simple example, one could just say that in general, the positivity of this term is a resonance condition, because in this case we have it just leads to can be derived from the this inequality that the tuning is less than a reverse correlation time. And to visualize our results, let us go to the exactly solvable case. Exactly, I already started. So this case is already was defined, but let us emphasize that for combinations of Lorentz peaks, we have one could solve the problem exactly in terms of finite number of ordinary differential equations with constant coefficients. So it's usually called pseudo-mode methods. It was derived, I think, here, and it is still developed in the literature, and I think this discussion is actually very close to if one want to generalize the results I have obtained for this simple model, one could just follow this generalization of the pseudo-mode method, because such a spectral densities leads to very good, well localized correlation functions. So actually, the possibility to approximate the spectral density in simplest case by Lorentz peaks or some over just by correlation by spectral densities which have only finite number of poles if we in the complex plane, then we usually could apply the technique I have derived. So for the it is possible for these combinations of Lorentz peaks in the simplest way by only considering the case described, for example, in Breuer-Petruccione book of the resonance case with only one peak. One could understand what is going on here more visually. Namely, here I have blue line is exact solution, and this orange line, the solution of the JKSL equation with constant coefficients, but with these renormalized coefficients defined in these which have participated in my main result. I have not yet given the exact formula for these coefficients, but I have do it a bit later. But it is not so important. Important is the following thing: that if you use just a solution of such a perturbative JKSL equation without the renormalization of the initial condition, then you obtain the solution here depicted the density the element of the density matrix in the excited state, actually, and it depends on the time in terms of gamma times to gamma. So it's time in the units of the correlation time. So it is easy to see that if you just consider the perturbative solution, but without this initial correction, then you obtain a solution which is differs from exact. But if you redefine this initial condition to, it is really important that you, but it seems a bit counterintuitive that you have to redefine this initial condition to non-physical state with the population of the excited state larger than 1. So the population of the ground state would be less than 0. So it's totally non-physical initial state. But if you paid this if you have done this redefinition, non-physical redefinition of the initial state, then you could evolve just by Gorini, Kossakowski, Sudarshan, Lindblad type equation with constant coefficients. And for sure, as I said, at the small time scale of order of correlation time, this approximation do not work. But just after of 2 or 3 correlation times, this corrected perturbative solution matches perfectly the exact solution. So just after 2 or 3 correlation times, we have very good approximation by the solution just of the JKSL type equation with constant coefficients. It is here something similar, but it is easy to show. It is easy to ask. But if it is important, maybe it is not better than usual weak coupling limit type JKSL equation. The answer is it is important because here is the green line is the usual JKSL type equation without any corrections, and so it's just the limit lambda tends to 0. And the orange line is mine perturbative solution. Here it is only in the second order of perturbation theory. So in lambda squared, we have no, if we have existed moments, we have no corrections of order of lambda, of course, and the first correction to the usual recoupling limit type GKSL is of order of lambda squared, and we have with maybe slightly not so perfect and larger times, but almost perfect coincidence of the perturbative solution and exact solution. But of course, we also have paid for it by the redefinition of the initial condition to the unphysical initial state. And of course, I'm so interested in long time dynamics because I think the problem of small time dynamics actually could be solved by many methods. For example, by just written the first terms of Dyson equations. So there are a large amount of methods to derive the dynamics for short times. And if you use one of these methods, you could just match their usual in serial perturbation theory, there are usual methods of matching the solution in different regions, and it is possible to match this the early time solution with my solution obtained by in the perturbation theory with Bogolubov-van Hove scaling, and then you could obtain this red uniform solution, and I think it is in this case almost perfect. It is very close to the exact, and it is only first correction to the perturbation theory, to the zero order of perturbation theories, that is to the usual GKSL equation. And in this situation, it was in certain sense inverse to the called slippage phenomenon for the Redfield master equation. Usually, there one could start redefine the initial density matrices as well, but usually it is possible. The situation is the following: you have to not go beyond the physical initial conditions, but go inside these initial conditions. And if we have non-resonance situation, that is, I have the tuning much larger here than the inverse path correlation time, then this situation analogous to the slippage also could occur here. So if we have non-resonance conditions, if we far from resonance, then we have to redefine. We have also redefined the initial density matrix, but it also would be a density matrix, but a different density matrix. And here we have slightly different behavior of the exact solution. Is also blue line here. We have prediction by green line of the usual GKSL type equation without any corrections, but my perturbative solution could, from one hand, it's on the one hand it could take into account this long time behavior, and of course, there is some non-trivial dynamics on orders of the correlation time, but I think it is almost obvious that at initial times, of the order of the path correlation time, the dynamics of the reduced dynamics of the system is highly non-Markovian. So it is not so strange. This is what is important, that just after 2 or 3 times of 2 or 3 path correlation times, we became to this perfectly Markovian dynamics. If I mean by perfectly Markovian, the GKSL equation with constant coefficients. So this is some initial dynamics, and then you have the of orders of 2 or 3 path correlation times, and just after that we could describe it by GKSL equations with, but we have to renormalize initial condition. And of course, this deviation of the exact dynamics is important from zero order dynamics is important. Maybe in this here you see the numbers here is not so important, but nevertheless. And of course, if we here I have used only one Lorentz peak. But of course, one could use several Lorentz peaks to obtain more non-trivial initial behavior. But after 2 or 3 correlation times, the system do not know anything about this non-trivial initial behavior besides this renormalization of initial conditions. So all these non-trivial initial dynamics contributes on the long times. Long here means just after 2 or 3 bath correlation time. Just after 2 or 3 bath correlation time, we all the information of initial non-trivial dynamics contributes only to the renormalization to initial condition and nothing else. So one could say that this non-trivial dynamics is locked inside the correlation time. It is exactly what have motivated me to all this discussion, because here I'm trying to say that it is non-Markovian dynamics, this initial non-Markovian dynamics, but actually it is completely positive divisible. So people who think of Markovianity as TP divisibility say that even here the dynamics is Markovian. But what motivates me for this discussion is actually this your work, your preprint on arXiv, where the Markovianity defines in terms of the coincidence of the Markovian correlation function defined by regression formula, and the exact correlation function defined just by maybe by regression formula with unitary dynamics of both system and reservoir. It is possible to write exactly the formula exactly of this form, but for unitary superoperators. Or it is possible to write it explicitly in this way for this case. And of course, it is possible to describe Markovianity in terms of correlation function. Actually, this discussion of the Markovianity in terms of higher order correlation function goes back to old papers by Lindblad and arXiv, Frigerio, Lewis. Actually, I understand this problem from your preprint, and I understand how it's related to other points of view on the non-Markovianity by this review. Well, and it is possible to formulate the following answer, that under the conditions of the above statement, actually the Markovian correlation functions and exact do not coincide. So it is this model actually is discussed in your preprint, so, and it is shown that the Markovianity in terms of correlation functions is broken, despite of the fact of that the dynamics is completely positive divisible. But the only if we do the same perturbation theory, then only contribution to the difference between exact correlation function and Markovian correlation function is exactly this renormalization of the initial conditions. So this Rm is exactly the Rm which I have used in the redefinition of the initial condition. So it is possible to interpret the situation interpret the situation in the following way: that yes, in terms of the correlation functions, the dynamics in non-Markovian, but all this non-Markovianity occurs at this very initial time layer of order of Bath correlation time. So, and after that, the dynamics do not contribute to this difference of Markovian and non-Markovian and exact correlation functions. So it is also possible to log the all contribution from non-Markovianity in this very earlier times of order of Bath correlation times. And it is, as I said, it is many people think that the initial dynamics is highly non-Markovian, and this is not very non-trivial. Which is non-trivial, that it is possible to log all this non-Markovianity at these initial times. And if one then just redefine the Markovian correlation functions by dividing by this renormalization condition, then of course the Markovian and non-Markovian correlation functions would coincide. So if you use this renormalization, then you could redefine. Then you could obtain if you actually this redefinition of the Markovianity in terms of correlation functions. And in strictly speaking, you are totally right that the dynamics is non-Markovian in terms of correlation function. But if you redefine this definition by this renormalization constant, then the dynamics become Markovian. And in this, if we use this long time perturbation theory, and in a similar way, it is possible to obtain the results for high order correlation functions, actually, because it's done in for m equals 0. So for exactly for the limit lambda tends to 0 without any corrections by Dunke, exactly in the with Bogolubov-van Hove scaling, and using his results, it's possible to understand that we have almost the same situation for higher order correlation functions. Well, maybe I have to say a few words about explicit determination of these coefficients here. Here is just to understand that they could be calculated explicitly in terms of moments of the Bath correlation functions, and this is why we need the existence of these moments. So it is just explicit formula for them in terms, and it is possible to write down, for example, first several coefficients which I call P0, 1, 2, and 3, and if you want to define from them the omegas and gammas, you have to just take the imaginary and real part of P tilde m. So it is possible to, for example, in zero order perturbation theory, the usual GKSL form equation leads to just imaginary and real parts of G tilde 0, which is exactly just zero order moment of the correlation function, and so on. And in a similar way, it is possible to recursively define all these renormalization factors for the initial conditions, and for the correlation functions, they are the same. This is first coefficients, and the last thing that I should say: what if the moment do not exist? What if here is an example of a correlation function? It is maybe not so easy to obtain as such simple as in the situation of combination of Lorentz peaks, the direct formula for the correlation function with finite zero moment, but infinite first moment. But if one takes the following correlation function, it is possible to define the spectral density for these correlation functions. So this is actually the correlation function. Chi is the parameter from 0 to 1. Then for this correlation function, due to the non-existence of the first moment, we obtain the half integer terms in the expansion, namely the not terms of only of lambda squared, lambda to the fourth, and so on, but also terms of order of lambda in the expansion of the density majors, namely for the populations we would obtain the corrections to the exponential dynamics, which turns to the which behaves when times go to infinity non-exponentially, but it's corrected by long polynomial tails, and the same for the coherences. So if we have violation of this condition of the existence of moments, we obtain deviation from this exponential dynamics. So for this just pure GKSL description, and we have non-exponential corrections to the time behavior at long times in this situation. And so I think so it is. This is why this condition of the existence of moments is totally needed. So here we have only zero moments. So we have described this dynamics by GKSL equation with constant coefficient in zero order, but it is impossible to write down any GKSL equation with constant coefficients already at the order of lambda. And we have we have non-exponential, we have polynomial long tails in such a case. Well, I think it's all what I want to say. Namely, it is possible to find all these results in these arXiv preprints, and the main results are the following. We have asymptotically described the dynamics of the reduced density matrix by GKSL equation with constant coefficients in this perturbation theory. The accuracy to which we could do it is defined by the number of moments which exist here. We have to redefine the initial conditions in this perturbation theory, and moreover, we have to redefine sometimes it to non-physical initial conditions. And it is possible to explicitly calculate all these coefficients with corresponding accuracy. So I think it's all. I would, if any questions.
dear Alexander. Thank you very much. It was a very, very interesting talk. So if any participants want to ask questions, there is not so many of us. You're welcome to raise your hand and we can ask questions. But before that, can I just kind of like, if I understand your talk correctly. So it was still in the, I think in the papers of Bogolubov that, you know, when you have dynamics of some large system and you look into the subsystem of it, what you will see that as it begins to evolve, it's purely Hamiltonian. Afterwards, you get some memory effects, so kind of non-Markovian dynamics. And after some moment of time, you get a pure kind of Markov description for the evolution of the system. And essentially, what your time T star is the point when you say that, okay, so there will be at some point in time where I can describe my system with the Markov approach. And at that moment of time, the generator is going to be given by your equation. Is it correct?
Yes, yes, it's correct. Of course, it's maybe for Bogolubov, all the things I'm saying would be trivial, but I think it's not so. Nevertheless, I think not so obvious for many other people. So, and for me, it's totally not obvious.
Yeah, I'm not saying that it's trivial, because many things which people I think are trivial, you know, they still needs to be done in the sense of, you know, like in the moment when you begin to do them, suddenly there will be many kind of things popping up which are highly non-trivial. And kind of the fact that you have a systematic way of constructing the generators which approximate exact dynamics, I think is very interesting. But the question is, which I have, like, if, for example, I consider not the one kind of system at the zero temperature, in this case, you have a one correlation function. But if I will have, for example, non-zero temperature, I can already have two correlation functions, or I can have more correlation functions. How this will modify your theory?
Well, I think well, we have one have to have finite moments of both correlation functions. If even one of them is have some infinite moment, then this would be broken. But actually, what is very important here is actually rotating wave approximation, because if we have rotating wave approximation for even more non-trivial models and non-zero temperatures, the situation would be almost the same. But I don't understand yet how the rotating wave approximation could. Is it possible to broke this good description in higher orders of the perturbation theory or not? So I don't not understand. So if you start with the Hamiltonian with rotating wave approximation, and then all this story it do not depend on the temperature. Independently of the temperature, the story would be almost the same. I don't have written it exactly in the paper, so I'm just finishing it now. But the story not very different. But I don't not yet understand how, if it's possible to broke something in this story by rotating wave approximation. So it's
okay. And another question is on the kind of the information theoretical aspect, is that now people begin to identify, like, then kind of within the open quantum system dynamics, the information flows, that which is going from the system to the bus and vice versa. So do you think that your moment T star will be related to the moment when the information never flowing from the bus to the system? So from that moment T star, essentially information only flowing into the bus.
Well, I think no. It is. This is why I said this. Your definition in terms of non-Markovian, in terms of correlation function, is essential here, because actually, nevertheless, maybe it's complex behavior, but is completely positive divisible. So there are no. So it is in terms of this information backflows. It's Markovian. It's all the times in this situation. So
okay. Okay. Interesting. Okay, and I think Camille wanted to ask a question. Let's allow him to ask the question. Camille, you're welcome to.
Hello, yeah, so thank you very much for this interesting talk. So in fact, yeah, I have the same question as Ilya. So what about the non-zero temperature bath? And yeah, I didn't understood exactly what you said. And so yeah, I just wanted to ask you, so what would be the difference if the bath is non-zero temperature? What's changed?
Well, the situation is the following. We just have to moments for both of correlation functions are finite. It is so if we have all moments of both correlation functions are finite, then we obtain the GKSL type equation in all orders of perturbation theory.
Okay.
Okay. Yeah. Thank you.
So the first infinite moment of between these two functions broke the picture.
Mm-hmm. Okay, but that's from, you know, while kind of listening to your talk, I was thinking about one of the papers, kind of a series of papers which were written by Filippo Derived with Francesco. I don't know, are you aware of those papers? Where Filippo is a big expert in kind of complex analysis and functional analysis. And what he was doing, he was taking, for example, this Garavay model, which is formally exactly solvable. And he was asking question, he was solving like an inverse problem. He was saying that, okay, if I want to have non-exponential decay of the populations, which spectral density should I take? And he identified classes of the spectral densities of the, I don't know, system bus interaction, which will lead to non-exponential decays. And he was playing the game of powers of the non-exponential decay. But do you think that the fact that you get a non-exponential decay, would that imply that there is no GKSL form?
Yes, sure.
In your sense, so that does it mean that the all correlation function will diverge?
Yes, yes, for sure. If we have divergence of certain moment, then after that we have maybe not necessary. Yes, you would maybe not necessary such a polynomial, but this is exactly the case of non-exponential decay. So if we have we have infinite moments of certain infinite moments, then the next correction would be non-exponential. Right?
Okay.
I should.
Okay, interesting. Okay, I do not see any more questions. So if the people still have a question, they can always send you an email and they can ask it. Yes, and I think we can thank you for this very nice and interesting presentation.
Camille has one more question, it seems, in chat.
Okay. Yes, sorry, I haven't seen that. And is the complexity increase as the dimension of the system increase, for instance, for harmonic oscillator?
I think no, because, for example, it is, if we use a zero temperature situation, then it is possible to reduce the harmonic oscillator into the rotating wave approximation to exactly this model. So we obtain exactly this situation. So I think no.
Okay. If I hope Camille is happy with your answer, and I'm happy to give it back to Francesco.
Yeah, no, I also just wanted to thank Alexander for the very interesting talk, and also for answering the question, one of the question of Ilya that I also wanted to ask. So thank you very much for that. That was really very. And I hope that you know, it seems that we have lots of overlapping interests. So I hope that we will stay in contact and maybe start some joint research project. That would be really very nice. Yeah.
Yes, yes, for me too, it was really, really nice.
That would be really very nice. And I know that I've forgotten the date now, but I think sometimes in the middle of January, we have the next talk by Anton. So then we will understand each other even better, yeah. And we can see it from there. Anyway, we will definitely read your preprint over the holidays, yeah, so that we are ready and understand all the details, yeah. And maybe as a last comment, I would just like to thank everybody for joining us today. And since it is our last webinar for the year, I wish you all the best for the festive season and the new year. And I know that your Christmas is a little bit after ours, but nevertheless, all the best to you as well. And try to get a vaccine as soon as possible. You in your part of the world, it's already available. Here we are still waiting. Yeah. So all the best to everyone. Yeah. Thank you very much again. It was really an enjoyable and interesting talk. Thank you very much.
Thank you.
Thank you.
Thank you.